Yeah, so I will just get started. One of the first things, so this is like how to do super resolutions with some epifluorescence setup that you have in-house. So the first thing is, what is single molecule imaging? I'm not sure how many single molecule talks we had. So basically, you take your sample. What you see over here is a HeLa nucleus, and you have some single molecules coming on and off. Then you do some background subtraction, and then basically you can identify all these single molecules, and then you can just take the sum of all these in different frames. So what you see on extreme right is the sum of these molecules. So this is basically essence of single molecule, to optically isolate single molecules and then sum them up to get a high resolution reconstruction. So whether it's PALM, STORM, DSTORM, or DNA paint, most of them have this concept, and how you do it differs from technique to technique. So the two most important elements for single molecule imaging that you should remember is precision and signal density. So by signal density, I mean you really need a high labeling of the sample to really know the unknown structures. For example, often you would be imaging some structures, right? Like if you are imaging structures above 200 nanometers, you can use confocal. But if you are using something from 20 to 200 nanometers, then you often don't know the structure. And then you really need some high signal density. So what I show over here is image of Erica, and where I sequentially increase the points from 10,000 to 10,000, 20,000, 25, 50 to 120,000. So what you see, the more I sample, you saw in the previous frame, right? The single molecules coming on and off. So the more I sample, the more fine features I can see. So for example, the eyes and the eyebrows of Erica, I can't make them out in 10,000. So you need some minimum signal density, right, to make out some fine features. So you would probably need 1 million signals to make out the fine features of the eyebrows, right? Or some more fine features of the nose. So this is very important, having high number of signals. And you will see in a lot of single molecule papers, people just don't have enough signal density. And for example, they will just take something like this and measure full width half maxima and then code. Or for example, do surf. And then you can get some crazy resolutions, right? So this is the most important aspect. And this is why DNA paint is so popular. The other aspect, like for DNA paint, right? You can get just any amount of signal, 2 million, 3 million. The thing is, you have to improve the signal density. Okay, if there are any problems, please pause me, because I don't see anyone saying anything. So just if the internet connection goes off or anything, Mark, Philippa, please interrupt
I think everything's fine at the moment, Kirti.
Okay. So with high signal density, it's equally important to have good precision. The thing being is, if your precision is poor, you will again end up with the confocal range. So for example, what over here I do is I slowly increase the localization uncertainty from 2 nanometers, 5, 10, 20, 50, and 100. So you see, if the sigma or the width with which we blur each point, if it gets bigger, right, you again end up with a confocal image. If you have too less precision and too less signal density, then also you will kind of be in this undersample domain. So you need, let's say with very low precision, you need very high signal density. Or in this case, you see, if I have slightly better precision, I kind of, cover up for the missing signals. So it's an interplay between signal density and localization precision. And this is what you need to do if you want to do single molecule imaging on any setup. So the problem is, classically, historically, people had these super sophisticated big setups ranging in price, like if commercially also, like Leica, Nikon, they were selling in around $1 million, and the home build ones were very complex. So the whole idea for super resolution was, do you need complex setups to do better? And are complex setups always better, right? So I had moved to US 5 years back, and at that time I had only this setup was available, because to use Leica confocal, and like I said, I needed 6 months training, and I had nothing to do except this microscope, which literally no one was using. So my whole idea was, can I turn any ordinary epifluorescence microscope into a super resolution? I started thinking, right, we have all these big sophisticated setups, but what do I actually need to do super resolution imaging, right? So if you think, there are mostly 4 important elements. You need a decent camera, not the fancy ones. Even an old 12-bit CCD camera will do. you need a good light source. I will come back to the light source. You need a high NA. You don't need like 1.4, 1.3 NA objectives will also do. And you need a good stage and a sample holder, because that's where the stabilization and vibrations you have to take control of. One of the problems with most epifluorescence setups is they come up with, they mostly have a lamp. Most of them don't have a laser. And then, because I had always learned you need lasers for super resolution, especially for STED, you need a highly monochromatic coherent light. But for single molecule, I thought all I need is, some minimum power density, right? Let's say 0.1 kilowatt per centimeter square. That's what Eric Bedzik quoted. And I said, can I generate that power with a, let's say, 200 watt lamp? And if I can do single molecule. So I looked at the spectra, and then I found, okay, this is mercury arc lamp. So you see some peaks around 400 nanometers, starting even from 350 all the way to 420 something. And then you have these peaks around 560. So all the old filters like, DAPI, TRITC, FITC, Texas Red, these were actually designed for these wavelengths for mercury lamp. So I said, okay, I buy a super powerful lamp, and I try to see if I can do single molecule with that. So basically what I ended up doing is I took this microscope, I put a rod below, some things to stabilize. I really don't know if it worked. And if you see the setup, there are a lot of small things. So I changed the lamp behind, and this is a very old computer. It has 2 GB RAM. So I was working with bare minimum that you can find in any lab across the world, no matter how poor lab it is, right? And of course, I got a new objective lens. The camera was this 12-bit CCD camera. So with these elements, I started working, and it took me a lot of optimization before I got these single molecules to come on and off. So I'm just showing a couple of frames and the trajectory of this molecule over 10,000 frames. So you can see it comes on and off several times, right? And this is the whole essence of single molecule imaging, that you can optically isolate single molecules. And once you do that, 90% of the game is over, because then all you need to do is improve the signal to noise and sum the images. You can do some of the post-processing to really improve the data sets. So this is just to show that you can get single molecule blinking with a lamp. And then from single molecules, you move to actually biological objects. So this is super resolution. Like, these are synaptomal complex proteins. So these are very wonderful structures, because with confocal, there are these 2 proteins which bring the homologous chromosomes together. And this is the Pacatine stage of meiosis prophase 1. So with confocal, you can't resolve the 2 complements of these proteins. This is very well studied with electron microscopy. So both the strands, so it's not known how thick each strand is, which is 60 nanometers, and the distance between the strands, which is around 150 nanometers. So these are very good biological objects, like beads, slides, other slides, all the slides that we saw. And so those are good, but you need some real biological samples, and especially good diffraction limited objects, right? Which have just the structures below 100 or 150 nanometers. So we could not only resolve the 2 strands, but also we could see the individual strands, which actually fits well with the EM data, which is we are hitting 60 nanometers with a lamp with an ordinary fluorescence microscope. And then we can do some interesting statistics, which is basically you can do all this full width half maxima analysis, what distances you are getting. So this is in this cross section of the image, how many photons. So we are roughly getting like 1,000 photons. So another thing with lamp is, over the years, like GFP, it emitted around 200 photons per burst, right? But over the years, with all these LXR dyes, Genelia dyes, the dyes have gotten brighter. And this is another advantage. Even with lamp power, you can extract enough photons, like roughly 1,000 photons per burst. We are getting a precision of around 17 to 18 nanometers. And if you think, I will come to the signal density, right? So if you have a lot of signals, you can actually even improve the resolution. But I will come to this point again in a bit. And if FRC is very popular these days, so we are hitting a 90 nanometer FRC resolution. And this is no filtering of data. This is just the raw data. So in the new, let's say, MinFlux, SimFlux, DNA paint methods, the new fashion is you take a millions of signals, right? And then you just take highly precise molecules. And then that's how you can claim, like, So let's say if I have a precision plot like this, then I only take a population with less than 10 nanometer precision, right? Then overall, of course, my data will be undersampled, but then I will get a very nice resolution. So when I was doing this and I submitted the work, the first criticism was, how do we actually know that there are these two strands, right? Okay, you can cite EM and others, but there should be independent validation. So unless you are a Nobel laureate or a big shot, you have to provide independent validation, right? Even if it's a low impact factor paper. So this was a big challenge. And what I do is I in turn came up with a framework to do correlative super resolution microscopy. So basically you start with confocal, then you do STED, and then you can do this laser-free super resolution microscopy. And here are the prices. Roughly like starting like confocal, market price is around $500,000. STED costs, maybe it's a bit less, but it was around 900K a few years back. And this laser-free is roughly 20K. So what's the problem? So there are a lot of behind the scenes technical challenges, because when you do STED imaging, right, there's almost a black hole. And that's the game over for STED, right? Because how do you recover STED bleaching, right? So then you move to another section, and this is the biggest bottleneck why people also don't do STED, because of these high laser powers in STED, which range in gigawatts, right? And there's no way you can recover this. So I think this was the most coolest aspect of this whole work, is to recover STED bleaching. So let's go back to the spectra of mercury arc lamp. So I use these peaks for exciting single molecules, right, around 560. Then I use these peaks for reactivation. So classically, let's say if you want to image Alexa 647, you will have a 640 nanometer laser, and then you have 4 or 5 nanometer laser for reactivation. I thought, okay, can I use these peaks for reactivation? And also behind the scenes, I felt photo bleaching is one of the most poorly understood and poorly studied concept in microscopy. People see a black hole and that's photo bleach, right? So I started playing with this and changing a bit of filters. And what I found is you could even recover $1 million STED bleaching, right? You can take this and then you can use these peaks in the UV and you can recover it. And then if you do a plot overhead, you can again see single molecules. Of course, the intensity drops, which you can also see in the single molecule plots. But this was I think the biggest thing, which if I have funds in future, I will investigate the reactivation with this deep UV wavelengths. And the coolest thing about this was I could just go on imaging like in DNA Paint, right? You can just go on imaging 2 million, 5 million signals. It's just like binding on and off, right? Similarly, in this case, with Alexa 594, the signals I could just continue imaging. So this is about 200,000 frames with close to more than 1 million signals, and I just could not bleach it. And each time I get this very reproducible structure and this very reproducible precision. So it's a very constant, reactivation of single molecules. So in the process, what I came up and which I'm very passionate about is towards like sequential correlative super resolution imaging. The thing is, the modern microscopy is moving towards 1 nanometer race, but I believe like we should be developing methods, correlative methods, so that if you have a structure, let's say you identify with a SIM or a STED microscope, right? So that you can independently identify with a localization microscope. So this is very important because most of the structures we don't know, right? Like how, except it's microtubules, synaptomal complex, even at nanoscale, their organization might change, right? So we don't know if these ends are joining in STED and SIM image, right? If that's for sure. So there has to be a bigger focus on correlative light microscopy, right? So that you can see like same imaging conditions, same labeling with STED, SIM, and this. So this is one of the things I have been working, and this is one of the protocols how you can go. You have to find the right dye. You have to find the like ideal photon count and structures you want to resolve. You can start with a confocal, do SIM, follow it with a STED, recover STED bleaching, get the single molecules, and then do the whole single molecule stuff. So this is the whole pipeline I have been working. And just to show on another, so these are lamb brush chromosomes. These are slightly.
Sorry, Kirti, I can't. I'm not sure if everybody else can. I can't see any of your slides at the moment.
Oh, I don't know that. So where did I lose?
Seems to have frozen on the deep UV peaks of mercury arc lamp.
Oh. This time the slide is Good. Can you see the slides this time?
Yes, I can see the slides.
And I think you lost me over here on UV lamp. You said, right?
I think yeah. Yeah. When that's where you stuck.
Yeah. So what I showed you is you can recover. You can do super resolution with any epifluorescent setup, and you are getting a precision of roughly like 16, 15 to 20 nanometers and a FRC resolution of 90 nanometers. Next, I jumped like on the importance of validating the structures, because most of the structures between 20 to 200 nanometers, you don't know them, right? So you need a correlative imaging setup to validate these structures. So one of the frames I ended up developing was correlative STED and single molecule. And one of the, so I think this is where we lost. So one of the things with STED, doing correlative imaging with STED, at least
saw this one, Kirti. I think you got a bit further than that.
Okay, awesome. So yeah, so we can recover the STED bleaching. What I mentioned is with this deep UV wavelengths of the mercury arc lamp, which is roughly range from 340 to 420 nanometers. And what I showed you over here is a section of a nuclear envelope, which is bleached. You can see a black hole, and then you can just recover it. One of the good things about this bleaching is it acts as a marker where you have your sample, right? Because it's pretty big. So this scale bar over here is 2 microns, so you can actually find this. And with this deep UV wavelengths, because in typical palm storm setup, you have like 4 or 5 nanometer, but now we have a whole range of wavelengths for reactivation, right? So this, what I said also was, photo bleaching and is one of the most poorly understood concepts in microscopy. And I believe instead of one wavelength, 4 or 5 nanometer, you have a set of wavelengths for reactivation. And I think this is one of the coolest things, because I could not bleach these synaptomal complex proteins over a period of 10 hours. So I kept imaging them. And as you see, the structure is very much reproducible, and also the precision we are getting is quite consistent. So this is what I'm now trying to advocate, is a pipeline for correlative imaging, so that let's say you identify a new structure with a STED, and then you can have like a SIM image of it and a STED image, and then you can follow it with a single molecule. And what you see over here is you have to choose the right dye. So let's say Alexa 594, it's a good single molecule dye, it's a good SIM dye, and it's a good STED dye also. So you can acquire a SIM image, then you can acquire a STED image. You can use the deep UV wavelengths for recovering the photo bleaching. Then you can have the single molecules coming on and off. And once you have the single molecule, you can reconstruct a super resolution image. So this is the hardest bit, how you get right number of molecules in each field of view. So basically, this is one last example. These are on lamp brush chromosomes in amphibian oocytes. So these are roughly 2 to 5 micron thick, depending on which part of the chromosome you are. So this is a confocal image. You can resolve the blobs. And then the wide field with STED, you start to see a bit more substructure in each of these. So these are chromatin domains. I won't go into the biology, but with this laser-free super resolution, you can even resolve what you can't typically resolve with STED. Another thing is a disclaimer, I'm not really a STED expert, so you might get better images, but I think these are comparable with published images on lamp brush chromosomes. Finally, there are a lot of, I'm also advocating low-cost open source hardwares. So including Auroch setup, Johannes Holbein, he maintains a list of a lot of open source hardwares, softwares. And yeah, that's the end of my talk. Thanks for listening. Actually, I see there is a delay. I'm changing slides, and it's
okay. I think that looks perfectly fine from where I was sitting. Thanks. Okay. Okay, thanks, Kirti. So I'm not sure if we have any questions immediately for Kirti. I was wondering though, you're using a lamp source for your single molecule. Does that lamp source bright enough to turn the molecules off, as you would normally in a sort of D-storm type of system with a laser? Or is it...
So Mark, what do you mean by brighten up? Like visually, does it look very bright, or?
Yeah, so I'm used to our systems whereby essentially you need to essentially bleach put most of your molecules into a dark state before you can really see blinking happening. And is that?
Yeah, exactly. That's the thing over here also. So initially you have a lot of structure, and then you have to wait for a minute or two to bleach a bit, and then you see single molecules coming on and off. So yeah, there is some initial bleaching involved. Another advantage with this amphibian nuclear pore sections were these are very thin membranes. So we kind of get optical sectioning also from them, and then we have to bleach less. So if you go in tissues, it will be much harder, but in flat samples, it's much easier. Yeah.
Okay, and Martin, who's clearly trying to delay the start of his own talk, was asking what the photophysical process that enables UV to reactivate the bleached molecules. I think you talked about this briefly. Have you got any ideas about what it might be?
Yeah, so basically, yeah, it's a long answer, Martin. Happy to chat on this. But again, these classic triplet states and how you recover molecules bring back. So if you think of photo bleaching, as a coma state. So I think with these different wavelengths, you have different conformations of molecules, which you can bring back. And that's why even if you, let's say, bleached one conformation, you can bring back the other one. So I think these different wavelengths, let's say 350 nanometers, will slightly reactivate in a very different manner than what 380 nanometer would do or 405 nanometer would do. So I haven't probed this, but there's a lot of cool things, and I'm happy to show you some of the photophysics things I have done later on. Yeah.
Okay, right. Thank you very much, Kirti. I think I think your analysis it's a very complicated. It's a very complicated question to answer, and there is no simple answer because there's probably many different mechanisms going on there.
And unfortunately, Mark, there hasn't been a lot of studies. So I checked a lot of literature, and I think this is one open area where more investigation is needed.
Yeah.